Hey there, welcome back to Calculus. Still experimenting around with good ways to make these videos. So instead of working on that small whiteboard in the bad light, I'm going to try to use this notepad where I've already made some notes and we can just kind of walk through them together. All right, so we'll see if this turns out a little better. You're looking at the outline of what I want to accomplish in this video. Last time we were looking at given parametric equations, what does their graph look like? We learned a technique called eliminating the parameter. There's also a link here, and it's linked off the Canvas page. I made a quick video showing you how you can use something like Desmos to graph parametric equations. So if you want to pause this and kind of look at that video, or just go to Desmos and have that kind of while we're working through this, you could be pausing the video and graphing these parametric equations that we're talking about here today as we go. All right, we can also talk about that online. So here's the outline. The general problem I want to be able to solve with you guys is, given a curve, how do I parameterize it? How do I come up with parametric equations that have that curve as its graph? Yeah, and we won't worry about doing all possible curves here, but rather just a few types. So I want to be able to, in particular, parameterize straight line segments. Straight line segments is one kind of curve from one point to another point. And in fact, the entire line is another thing I would like to be able to parameterize. Graphs of functions. Y is a function of X, maybe even if X is a function of Y. It's very easy to parameterize those things. And then circles. Here, the fourth and fifth things are really the same. I want to be able to parameterize any circle, any center, any radius, or a piece of it, an arc of the circle. All right, so that's what we're going to try to accomplish in this lecture. So let's start with line segments. Parameterizing a line segment. It's a directed thing. It's a line segment from one point to another point, and the direction matters. So I'll always indicate that, like we did in the other video with arrows on the curve. So here I've drawn my 2 points, and I've indicated the direction of the line segment. And so how to find this parameterization? Well, here's the idea. Kind of like when you calculate slope, you start by taking the changes in the x and y variables. So I'll let delta x be x2 minus x1, delta y is y2 minus y1. And notice in both cases, I'm subtracting in the right order. I'm subtracting the end point minus the initial point in both of those changes. And then for a number that's between 0 and 1, I just multiply those changes by that number, adding the result to the initial point, x1 and y1. So if you think about what those two formulas are going to do as t grows from 0 to 1, the t variable here, you're going to add this difference to x1. So when t is 0, you get x1. By the time t gets to 1, you've added the entire difference, so you get x2. It's the same thing in the y coordinate. So you can literally just kind of put these somewhere where you can refer to them. They're perfect formulas because, again, the problem is, what am I given? I'm given 2 points and I want the line segment between them. Well, I can write that down given the 2 points. If I know x1, y1, x2, y2, I can write these formulas down. The parameter will always take on the values between 0 and 1 using this parameterization. Let's look at a really quick example. See if we can leave the formulas in view. So how about if we took these 2 points? I just kind of randomly made them up, 2, 5 and minus 3, 7. Okay, well, you got to compute your differences, and you need to do it carefully. The change in x, the end point is -3, the x coordinate of it, so I subtract -3 minus 2. Same thing with y. So if I get the order of the subtraction wrong there, I'm going to get the wrong change in x. I'm going to get the wrong formulas. Here, my change in x is -5. My change in y is 2. So looking at the formulas above, I can write down the parametric equations. It's the initial x value plus the change in x times t, the initial y value to change in x times t, always taking t between 0 and 1. Yeah. If you tried that Desmos thing, stop this video right now, type those parametric equations into Desmos and check it out. See if it, Desmos won't show you the direction. It's just going to show you the line segment, but we got the direction correctly. Correct. Cool. All right. So that was the first thing, line segments. Second thing, how about the whole line? the infinite line, if I don't just want a segment. Once again, it's a directed thing. So when you're talking about parameterizing a line, you have to specify which direction do you want that line to get swept out in, quote unquote. So here I'm going to be going from x1, y1 to x2, y2 again. All right. Well, we know how to parameterize the segment, same parametric equations that we were just talking about. If you want the entire line, all you have to do is loosen that restriction on t. You want the entire line, you just let t go from minus infinity to infinity. And then, oops, I'm getting a message. Then you'll not just get the segment, you won't just get the points between x1, y1, and x2, y2, you'll get the entire line. In fact, we can kind of understand the geometry even a little bit better. I colored in this picture. I'm showing you over here, for the parameter values t equals 0, well, you'll get the point x1, y1, and for t equals 1, you'll get the other one. Well, the segment between those is what we were parameterizing before. But if you allow t to, say, be any positive number, well, then you sweep out this part of the line that I've highlighted in red there. That's kind of the positive half of the line, if you like. Positive values of t, the parameter, will give you points on that red part. Negative values of t, conversely, will give you values on the line, points on the line where I've highlighted it in blue. So it kind of, this direction, it gets inherited from the number line. You think of this line you're parameterizing as the t-axis kind of put into the xy plane by your parametric equations. Okay? Let's talk about how to parameterize the graph of a function. Graph of a function, I've drawn my usual kind of generic picture here. Once again, it's got to be directed. So I'm going to be parameterizing these functions so that the input variable x is increasing. The way you're looking at this picture here, I'm parameterizing it so that I'm looking at the graph swept out left to right. Okay, and how to parameterize a function? Well, on a function, let's just recall for a second that every point, the input coordinate determines the output coordinate, right? So one number, x, down here determines that point because you have the f of x to tell you what the y value is. Well, we can take advantage of that. If you're trying to parameterize a curve, we just want points on the curve, x comma y, to be determined by some other single number, the parameter t. Okay, well, let's just take x to be the parameter then. The parameter can be x, and then you let the function tell you what y is. So parameterizing the graph of a function is really just sort of a psychological point of view switch. You just think that some number, the parameter, determines x and y, but x is just the parameter. It'll always give you a parametric way to think about the graph of a function. All right, and again, note the direction, left to right. Let's look at an example. I want to parameterize the, say, decreasing exponential function e to the minus x over some interval. This would always be the ingredients. Somebody's got to tell you, what's f of x, what's the interval? Here I've drawn the picture. I hope it looks familiar, that that's what e to the minus x looks like over the interval from -1 to 1. I put a little arrow indicating the increasing input variable direction. And the recipe is simple. You take x to be t, y is f of t. Let t go from whatever interval you want it. Those are parametric equations for that graph. Stop the video, plop them into Desmos, be amazed. It'll graph it. Kind of cool thing is that the same idea, you're going to have a couple of these in your homework problem. You can parameterize curves that aren't functions of x, they're functions of y. Here, I've got an example kind of turning your head sideways that I'm looking at the graph of x is equal to sine y. Yeah, that's not, that thing doesn't pass the vertical line test. It's not a function of x, but it is a function of y. And I've put the arrows on there indicating that I want it to get swept out in the increasing y direction, that is from bottom to top. And we can take advantage of the same thing. This time we just say, well, let y be the parameter, because that's the kind of independent variable, the deriving variable. And then you let x be, well, if x is the sine of y, then you let x be sine of t. Take t in the right range, check it out. That's not a function. You cannot make that curve as the graph of a function of x, but if you go to Desmos and graph this thing parametrically, then you can. You can graph that curve in the plane because you're not graphing it as a function of x. It's not a function of x. You're graphing it parametrically. Okay, we got kind of one more piece of work here. Trying to keep these videos as short as possible. I know I'm talking fast, but you can slow it down and stop. The last problem I want to be able to solve is how do you parameterize a circle with a given center and a given radius? All right, center is HK, radius R. How do I parameterize it? Let's start with a special case where the center is at the origin. So I've drawn here a nice circle. I want to give a shout out to Vinny in our class for teaching me a little bit about how to use this notepad software. So thanks, Vinny. I hope you're proud of your student. But what have I got here? I've got a circle drawn with its center at the origin. I didn't label my axes, but I can do that for you. That's the x-axis, that's the y-axis. So they cross at the origin. My circle's got a radius r. I've labeled it there. And what am I trying to do? I'm trying to say, well, what are these x and y coordinates as a function of some number, some parameter? And a very natural parameter here is the angle. Every point on that circle is determined by an angle, t, where t is in that interval. If you include 2 pi in there as well, then you'll just describe the point that corresponds to the positive x-axis intersection there twice. T equals 0 and 2 pi, but that's okay. So I'm trying to say what x and y are in terms of that angle. Well, that's just a trigonometry problem. Yeah. In trigonometry, we look at this picture all the time. If I kind of highlight this triangle I'm thinking about in red up there, and then I'll just sort of highlight it down here, just think I've like extracted it out of that picture. Yeah. Well, in trigonometry, if that angle is called t, then we're taught that the cosine is the ratio of the side length adjacent to it to its hypotenuse, and the sine is the opposite. And if we solve those things for x and y, well, there you go. X is r times the cosine, y is r times the sine. Take t between 0 and 2 pi, and you'll parameterize that circle counterclockwise exactly once. If you allow t to take on other values, then you can go around the circle more than once. Typically, when we parameterize a curve, we sort of want it to get swept out one time. And I have accomplished that again, except for this point. The point right there that I'm labeling, it would have 2 parameter values, t equals 0 and t equals 2 pi. Otherwise, if you take t in this range, every other point on the circle will be swept out once. Okay? But we didn't want circles only at the origin. We said we wanted their centers to be arbitrary. So what do? Well, if you want to move the center and hence the whole circle, you should shift the x coordinates by h and the y coordinates by k. How do you shift them? Just like you do with functions. You add those values. So here's the final answer. You want a circle centered at the point h comma k with radius r. Okay, take x to be h plus r times the cosine of t. Y is k plus r times the sine of t. Let t go from 0 to 2 pi, and you'll traverse that circle counterclockwise precisely one time. So there's a little picture down there for you of what we've parameterized. Again, stop this thing, go to Desmos, pick an h, pick a k, pick an r. It's fun, it's cool, it's a cool way to draw circles. All right, let's look at an example. I owe you an example. So let's parameterize the circle. I just kind of randomly made up this point, minus 3, 7, picked a radius of 9. Here I tried to kind of sketch what I'm doing for you there. I labeled some of the other points just to give you a scale of the radius, but the center here is minus 3, 7. I was just picking these other points to kind of draw the picture right. And well, let's try out this formula. I don't think I pre-wrote it. So let me try to write it down now. So what did we say? What am I referring to? I'm referring to this business. That's what you want on your note card. Well, your virtual note card now. maybe this thing, I'll send you the PDF. This can be your note card. But what do? We take, for x, well, you take the x coordinate of the center, that's minus 3, and you add to it the radius, 9 times the cosine of a number called t, thinking of it as an angle. And you do the same thing for y, except you use the y coordinate of the center. The radius is still 9, and y is the sine function. And if we let t go from 0 to 2 pi, we will traverse that circle counterclockwise precisely once. All right. So I hope you'll try out. Well, I'm going to do one more thing. So let me not sign off here yet. I wanted to ask one more question. How could I parameterize just a piece of that circle? You know what I mean? What if I don't want the whole circle? I wrote the top left quarter. Let me tell you what I mean by the top left quarter. Maybe I just want to parameterize that part in the same direction. So how could I do that? Well, the good news is you don't need to change X and Y at all. X and Y are telling you that you're on the circle. This T value range is what gave us the whole thing. So thinking of T in this picture here, it's still just the angle from a horizontal line. So if you want to get that just top quarter of the circle, all you have to do is restrict T. Restrict T to what? Well, what angle would this top point on the circle correspond to in the usual trigonometric sense? Straight up, that's when the angle has become 90 degrees. So in radians, we'd want to take T to be at least pi over 2. But then this point down here, well, that's when the angle has become 180 degrees or pi radians. So by choosing T in this range, if you're in Desmos, do it, play around with it. You can get little pieces of the circle by taking the corresponding angles of the piece that you want. All right, so that's it for this lecture. Thanks for watching it. I hope it was good. What are your tasks? Your tasks are to look at the activity sheet, complete it, send it to me so I know that you're participating and moving along. You can also send me any questions that you have, or we can meet online and talk about them. And then there's the book homework. I'm working on a way to get that book available to you. If you were checking it out from the library, the publisher has made it available online, I think for free for everybody until May. So why do this activity sheet and the book homework? Well, because it gives you a chance of practicing all these skills. Yeah, so these kinds of curves we'll want to be able to parameterize. Okay, I'm going to cut this short. Thanks for paying attention, and we'll talk to you when we talk to you.